Let's talk about the library method, and the particular part we're going to focus on is deconvolution. The definition of deconvolution is shown here in a generic way. A more precise definition would be process of computationally separating colluting mass spec components and their associated spectra. I do want to stop for a moment and acknowledge the work done by NIST and Steve Stein with his group that happened in the late 1990s that popularized the deconvolution approach, especially with GCMS data. And you'll see we've done some improvements, but largely they share the same approach. So here we are in the library method under the deconvolution tab. Let's take a look at resolution, retention time, window size factor. And you can see there's a number of values here that are important in getting that matched. If it's too narrow, you can miss the peak. If it's too wide, you get a lot of junk peaks. So let's take a look at the definition of that term in the quantitation unknowns data set. Window size factor, a dimensionless scale, and it's like resolution in AMDIS. It's both a blessing and a curse. You need to get that parameter correct, otherwise you will miss or get too many peaks. So we vary that parameter and pull out the best hit, which is the hit that's given us the best library score compared to the library entry, giving you the best answer. Next, in the deconvolution pane, let's take a look at the extraction window. So the extraction window for unit mass is typically 0.3 and 0.7, a little wider on the top because of the atomic masses tend to be leaning in the positive side. If you're doing accurate mass, you'll want to move to parts per million, and that typically would be, let's say, 25 and 25 in terms of a window that would see the components you're interested in. There's a choice here about using integer mass values. So if you happen to be searching against the NIST library, which has many nominal masses entered, this can help you get better matches in terms of the window of your compound, the tuning of your instrument, and the entries in the NIST library. Worth mentioning that use integer MZ values can clean up the mass assignments in an isotopic cluster. Because of the shifting and possible binning effect, if the window picks up pieces of the ion cluster, you'll get unexpected ratios where using the integer masses tends to clean that up. In the deconvolution pane, let's take a look at component shape. So there are a number of choices here. One is to use the base peak shape, the strongest ion in the collection of ions, to determine the model peak shape. I typically use the default. Then there's the sharpness threshold. So let's take a look at that definition. That would say that if that peak doesn't have a sharpness of 25%, we're going to reject it. I typically keep that default so that I don't get junk peaks in my component and spectrum. And if we look at how that appears, here is a ion peak with the model peak. I can see the TIC, and there is the component, which is the shape of that aggregate of all those ions. At the bottom of the deconvolution pane in the library method is a knob that allows me to adjust the ion peaks. So taking a closer look at that, it allows me to establish a minimum number of ions that must exist in order to look at a component. Maybe that's 5. And also the maximum number of ion peak shapes to store. So if I say there's really 10 ions in the kinds of compounds that I'm interested in storing that I want to use in these components, I could limit, I would save space, and get me more directly to the answer. So those are knobs that exist in the deconvolution pane. Thanks for your attention.